name is Ryan Marciniak, and I'm really glad to be part of the RAS stream tonight. We have a special guest with us, a good friend of mine, a great scientist, an excellent astronomer, and a darn good communicator, Jesse Rogerson from the Canada Aviation and Space Museum. He is a science advisor there. Say hello, Jesse.
You make me feel so good. I don't know if I was like an amazing scientist, but I definitely did science. So I definitely did that, and I can say for sure that I was and still am sort of a scientist. So yes,
you have graced the pages of the scientific encyclopedia.
Yeah.
As you can probably tell, our usual host Jenna is not with us tonight, so she's feeling a little bit ill. So we're going to hope that she gets better fast and is back here doing the live streams again and taking charge and being the great host that she is. But instead, she's left all the hard work to me for the evening. So I'm going to be acting as your host. We're going to talk about a few really fun topics that we had planned out, and then we're actually going to hear a lot from Jesse about his research, which I'm not going to spoil, but well, it was on quasars, active galactic nuclei. So we're going to talk about that. That's kind of cool.
I can give you
some other stuff to talk about. The meteor shower that peaked just this morning. Hubble's 30th anniversary is coming up in a few days, which is kind of neat. So we've got picked a few favorite Hubble images, and yeah,
sounds like a good show.
We're just gonna talk and have some fun over the next hour. How are you doing, Jesse? You having a good day there?
Oh, it's great. It's so busy. So for those who've never seen me or met me before, I live in Ottawa, which is the capital of Canada. And we have a great RASC crew here. The crew for RASC here in Ottawa is just a great group of guys. Mike and Chris and Tim, they're really, really cool. They work really hard. They put on, and the cool thing is that they run their meetings out of my museum. I work at the Canada Aviation and Space Museum, and they do their meetings there. And we even get to do a few star parties once in a while at our museum, which is really cool. I'm an astronomer by trade, so I did a grad school in astronomy, and I studied quasars, as Ryan talked about. This is actually sort of familiar to me because as an astronomer for quasars, all of my research was done with big telescopes in Hawaii, and I never went to those telescopes. So all of my observations I did just like this, sitting at a desk and waiting for the data to come in. I didn't actually go and look through telescopes for my research. I did a little bit for other people's research that I collaborated on, but for my own personal grad school, I stayed in and I typed on my computer and got my data that way. So it's actually kind of a bit familiar for me to be isolating while I'm star partying, I guess.
Well, isn't that just observational astronomy in a nutshell now? Like, I don't know about you, but when I was a kid, I was like, oh man, I'm going to be an astronomer. I'm going to go use the biggest telescopes in the world and do some really cool science and look through those eyepieces. And then, you get into graduate school and it's like, oh, well, your data's already here. Have fun.
Totally.
In front of this computer for the next 4 years.
It was kind of a little bit of
it is cool to look at the imagery and the stuff that comes through it. A couple hellos in the chat. Hi, Phil. Hi, Fred. Hey, Andrew. Hey, Chris. Nice to see.
Yeah, Chris, the guy I was talking about. I said the RASC crew in Ottawa is really good. That's the guy. He's awesome.
So, Chris, you can stop listening. You've heard everything about Jesse already. You don't need to join it. Now, of course, you're welcome to join. We're going to have a lot of fun over the next little bit. So,
wait, one thing, Ryan.
Please, yeah. I think I cut you off in the middle of your introduction, so please go ahead.
I was done. But that thing you said about joining grad school and then here's your data, you don't have to use telescopes. That's totally what happened to me. However, my supervisor, Pat Hall, whom you've met, he made it a point to send me to telescopes. And I'm going to tell you, I could tell a really great story about that. I'm sure I've told you before, but I'm sure everybody else would want to hear this. Okay, yeah. Here's the story. So when I went to grad school, I had very little experience with telescopes. I did an undergrad in physics with you, Ryan, at McMaster University in Hamilton. We did a little bit of telescope work, but not a lot while we were there. And so I was very green when I went to grad school at York University in Toronto. And so I showed up, I started working on data that was already available, just like you said. And then Pat said, you know what? I have some collaborators down in Tucson, Arizona, and you can go down there and you can learn how to use a telescope with them. And I was like, yes, this is great. It's a 2.5 meter telescope. It was a big thing. We were going to be looking at quasars. It was fantastic. So I flew down to Arizona. Everything's looking good, right? There's going to be another guy there who knows how to use the telescope. He's a postdoctoral student. He already has his PhD. He's used the telescope a million times. He knows what he's doing. He's going to teach me how to use it. I arrive at the telescope in the morning. That night, I'm doing observations, and that guy didn't show up. It's not his fault because he had to do emergency dental surgery. He had a big problem. He had health issues. He had to go fix them, and I'm glad that he took care of it. But it left me completely stranded on a mountain in the middle of Arizona, completely not sure what to do. And that was my very first time ever using an actual professional telescope. Luckily, both the postdoctoral student in my research group, Paula Rodriguez Hidalgo, and Pat, my supervisor, both stayed up late with me on Skype, talking me through how to do things as I read manuals and like played around trying to figure out. I did actually get data on my first night, I'm proud to say, with their help. But man, that was a crash course in astronomy right there.
Amazing. Hey, you had a lot coming at you, but you figured it out. You got it done. That's pretty awesome, man.
Yeah.
Just one quick note, anybody who's in chat, feel free to ask any questions about anything that's going on with astronomy, with the sky, with what we're talking about. This is a great opportunity to ask Jesse questions about his research once we dive into that a little bit more as well. But thanks for sharing that story, Jess. I like that one a lot. It's nice because I know all the people involved too.
So I was like 21 years old or something. I was really young.
Yeah, it was just in the beginning, eh? It was really early on.
Maybe 22. I don't know.
Right on. Well, we got to give a shout out about Earth Day, which is today, right?
Happy Earth Day, Ryan.
Happy Earth Day. Sounds like you're saying happy birthday, but it's everybody's birthday. It's the Earth's birthday.
It's the Earth's birthday.
Right? Yeah. Oh, question from Mike in the chat. Has Comet Atlas disintegrated yet? Ooh. I'm glad you asked that because we're going to talk about it. And now that we've given our Earth Day shout outs, why don't we just jump into it? Why don't we just
wait, before we get to that, one shout out I want to say about Earth Day. So since it's Earth Day, I think we are astronomers. Everybody here is in an astronomy club. We like to look up, right? And we like to look out from the Earth. But there's a lot of we all know that there's a lot of great stuff that's looking down at the Earth. And the RadarSat constellation mission that was launched by the CSA early 2019, I think. In mid to late 2019, it was fully commissioned, and now it's taking data, and it's 3 telescopes that are on a polar orbit, three satellites that have synthetic aperture radar that are on a polar orbit, trailing each other every 30 minutes. One goes overhead, and they radar image Canada, all of Canada, once every like 4 days or something like that. It's a really great constellation of satellites. It provides incredible data to lots and lots of different industries, and it's just a great thing to have, and to remind ourselves that on Earth Day, things that look down are really important too.
Yeah, it's true. I mean, you look at the Canadian Space Agency, a huge part of their work is Earth science for Canada, right? It's similar with NASA in the United States. We're doing astronomy, but that's just a small portion of it, right? It's there's a lot more to it.
And in Canada, it's really tiny. I don't even know if they have a full astronomy stream there anymore. However, there's some good grassroots people in the professional astronomy world that are really pushing forward this telescope idea called CASTOR. I don't know if you've heard of CASTOR. Yeah, you've probably heard of it. This potential space telescope that Canada wants to build, the professional telescope, the professional industry, CASCA wants to build.
Yeah.
That would be sort of like a Hubble 2.0. It would be an optical telescope, optical UV. It'd have a wide field. It would have various color filters and spectrometer, that kind of stuff. It'd be a hell of a telescope. So the CSA is aiming in that direction, maybe.
And important because it'd be primarily Canadian scientists who would get to use that telescope time, right? Absolutely. As all astronomers, we apply for time with Hubble, as we will with the James Webb Space Telescope when it launches. But a telescope
5% of time on that.
Yeah, there you go. So we get 100% of the time Canadian astronomers for a telescope that is built in Canada for our purposes. So pretty cool stuff. I hope to see that move forward, right? Yeah. Okay, Comet Atlas.
Let's do it.
Okay, I've got a couple things you can look at my screen for.
Ooh,
this is a
data.
light curve of Comet Atlas. So a light curve, for those who don't know, is basically they measure the magnitude of the comet day by day by day.
The brightness.
Thank you, brightness of it.
Just for people who don't know what magnitude means.
Yeah. And so they basically get a plot and they can predict how a comet's going to brighten. That gray curve is kind of what comets typically look like as they brighten, as they get closer to the sun, right? Comets typically have really elliptical orbits, which means they start way out in the outer solar system and come in far closer than Mercury to the sun, buzz around the sun, and head back out. Now, Comet Atlas, if we go up a bit, you can see its orbit here. So this was its orbit. You can see where it is right now. Now, it's kind of hard to see because it is three-dimensional, but hopefully that helps a little bit. I know it's tough with the way my screen is too, so I'm going to
No, I like it. It works.
Share it.
Yeah.
So as the comet's gotten closer to Earth, closer to the sun, it heats up, it off gases, it grows its tails. And this comet was exciting because it was supposed to be the brightest comet. I mean, as many comets are, the brightest comet of the century. It was going to get up to a magnitude that would have put it as bright as the planet Venus in the sky. And if you know how bright Venus is, or if you don't, you can go outside and look at it right now.
Right now.
If you're in, I know you can see it in Ottawa. Jesse was showing it to me, and I can definitely see it from here in Toronto. So for those of you across the country, I hope you have clear skies as well, as always, so that you can go and see that. So what ended up happening though is that the comet all of a sudden stopped brightening. It was heading on this curve where in May it would have been at its peak, as you can kind of tell if we go down. You can see the bottom of the image there, month by month. But it started to disintegrate. It didn't get any brighter. Something weird was happening. The coma, which is kind of the core of the comet around the tail, or around the comet itself, started to broaden a little bit, which generally means it's starting to break up. And sure enough, that was exactly right. It did start to break up. And the astronomy picture of the day from a couple of days ago was this. You see that right there? This is Comet Atlas, Comet 2019 Y4 Atlas. There's not just one piece. There's actually about 4 or 5 pieces there that you can probably count out yourself.
Yeah.
And see that the comet has in fact completely disintegrated. Well, at least into chunks anyway. And so as you can tell by the light curve, right, we're starting to see that the brightness is decreasing. We're down to a magnitude of maybe 9.5 or 10 for those who do observing. That requires a pretty big telescope to be able to see at this point. It is located in right around Ursa Major, and you can kind of take a look at where it is. You can see it's right here, is close to the constellation of, I think that's Cepheus right there. So just a little bit near Cepheus, kind of beyond the Big Dipper over here. So I'll show you that on Stellarium as well, because why not? Because I have all these things to play with.
So just to say, ask you again, did you say that it's now dimmed to 9 or 10th magnitude?
Correct.
Oh yeah, that is pretty dim. That's unfortunate. But that is not, most backyard telescopes should be able to get something like that, right?
Yeah, I think so. So there's Ursa Major, and the comet is kind of in this region right here.
Oh yeah, okay.
There you go. So we'll come back to me. But there you go. That's basically what's happening with Atlas. Is it's disintegrating as it rolls in closer to the sun. That's only going to get worse. It was originally thought that the comet was that Atlas was part of another comet that broke off a couple of chunks, and so it was apparently a chunk of this other comet.
What, really?
Yeah. I can't remember what the comet was specifically, but
presumably it shares a similar orbit.
Yeah, exactly. And that's actually, I think, how they tracked it down. Okay. That it was part of this larger comet that has a regular period and continues to come back. So this chunk came all the way back and is slowly breaking up. And once it goes around the sun, it's not going to come back.
Yeah, it'll probably, with it being broken up into small little pieces, the sun is going to be able to wreak havoc on it. It'll fizzle away and go. And it makes me wonder, so what governs the compactness of a comet, because I'm trying to think of like what would cause a comet to disintegrate. Well, it's probably because it's not very compact, or or a better way to think of it, maybe it's a few small pieces that did kind of drift together and fuse in some way, but those little pieces only have loose connections between each other, and then so when they get warm again and they sublimate, then those pieces can fall apart, but maybe the chunks are denser. But so when you see things like this happen, when you see a comet or an asteroid spin apart or stuff fly off an asteroid like it's happening at Bennu right now, you're getting really cool indications of the compactness and the density and the structure of something. You can think of something that's super dense and compact and is going to stay together no matter what, or you can think of the loose rubble piles that we tend to think of asteroids can be. And comets can be maybe loose rubble piles as well that are sort of tenuously conglomerated together. And then when you get an outside force like a spin or like the sun, it's easier to break it up.
Yeah, exactly. I mean, the sun has a lot of pressure too. Chris is just pointing out in the chat that every time a comet's built up, our expectations as the best in a long time, it seems to break up early and disappoint us. The one that I think of is Comet Ison. Do you remember that one? I bring this up. Honestly, okay. I was so hurt by this. I bring it up literally every time I do a stream now.
It holds a special place in your heart, eh, Ryan?
Well, yeah, there you go.
Yeah.
So I think it was 2015 that it happened. January rolled around and this comet had been discovered, and they said, oh, it's going to get close. Its closest approach, it's going to go behind the sun in December. And then when it comes out the other side, it's going to be perfect. It's going to be this gorgeous, beautiful, bright comet. And so I was super hyped up about it. And we talked about it. I was at the Science Center at the time, and we talked about it the whole year. We were so excited about it. And then the comet goes behind the sun and never comes back. It completely burned up behind the sun. That was the last we ever saw of it. And
so think of all the children that you lied to that year, Ryan.
Thanks. I have thought about that.
I'm kidding. Because this is a really important point to communicate to audiences at the Science Center, audiences here, audiences all over the place, that comets, and as Chris is pointing out, and as Ryan is pointing out, comets are highly unpredictable, and we can try to predict them, but we don't always get it right. In fact, we almost never get it right.
Mm-hmm. That's true.
Yeah.
And comets are actually going to lead us to our next topic. The Lyrid meteor shower peaked this morning at 4 a.m., I think it was. But it's a perfect time to have a meteor shower because it's a new moon, right? So that helps us out a lot, doesn't it?
Oh, fantastic. I did notice that it was a new moon when I looked at my calendar, but I forgot that the whole lining up with I didn't even think about the meteor shower this time around.
Yeah. Well, I mean, let's be honest, Jess, we live in cities, and even with a new moon, any significant amount of light pollution makes it really tough to view a meteor shower. But I'm going to pull up Stellarium again so we can take a look at where the shower is. So this is looking east. This is from Toronto, by the way, but it's more or less. We all know.
We did have there's someone who said that they were from Alabama, Birmingham.
Oh yeah, that's right. Yeah, fair enough.
Cool. I've never been to Alabama.
Birmingham. Well, sorry about that, Fred. I'll try and be a little bit more generalist instead of just assuming everyone here is Canadian. At least you can tell I am by the apology.
Thumbs up from Fred.
Oh, perfect. So, as long as you can see Vega in the constellation Lyra, a bright summertime constellation, the Lyrids are kind of between that and Hercules. So if you can bring up the name, you can see Lyra and Vega and the Hercules. The radiant, which we call the point that the meteors in the shower appear to come from. The radiant of the shower is between Lyra and Hercules, so close to the bright star Vega. But typically when you're going to observe a meteor shower like this, you don't want to just stare at that point. It's good to kind of lie down on a blanket or in a reclining chair, if you can, outside, and kind of look in that general direction. In this case, it appears to be east-northeast, I guess. And so if you kind of look in that general direction, any meteors that streak over your head will be visible as you kind of work your way through. We also got a note in the chat from Marie. You can also listen to Meteor Pings at livemeteors.com or sdrmusings.com. That's kind of cool. I've never checked those out. I should.
I wonder. I almost want to go check it out right now. By listen, what is the sound that's being made? Is it being something transferring through the atmosphere? Or is some I'm trying to think of what is actually being measured.
Maybe, I don't know.
I'm going to look into
I haven't looked at the site, so we got to check it out.
Attila, maximum magnitude of a comet is inversely proportional to news coverage in non-scientific media.
Yeah, there you go.
On the meteor shower note, there's a gentleman that works at my museums. His name's Pierre Martin. He is a die-hard meteor shower expert, I would say. What he does for almost every single major meteor shower, he'll go out and do observations, but not just to, I'm sure he enjoys it. He loves doing it, but he's also scientifically measuring it. So he'll go out, especially in the winter, he'll have a full like sleeping bag, goggles and stuff. He'll have a counter, and he'll have a recorder, like recording his notes. He'll make notes with his voice, and he counts. He goes out and he counts all night, all the meteor showers that happen. He gets incredibly accurate measurements of all the meteor showers that are happening. I gotta send him an email and see if he went out for the Lyrids this time.
That's fantastic to get a sense of the rates.
Yeah.
Rates.
I wonder, do you know, or maybe anybody, I'm sure someone in the group here knows the origin of the Lyrids?
I can tell you. I did a bit of research. It's, excuse me, C1861 G1 Thatcher is the comet.
Thatcher.
It's got a period of about 460 years. But so fun fact about the Lyrids, since I did my research now. So this meteor shower is one of the oldest recorded, and has been measured for up to, I think it was 2,700 years.
Whoa!
And so that got me thinking about how, these things happen, and how meteor showers are basically these debris trails from comets. Well, it got me thinking that, if the comet every 460 odd years comes around closer to the sun, and it starts to off gas and lose bits of dust and kind of fuel that meteor shower, it would have to keep going around again and again to fill a little bit more of its orbit with this debris. That now, as the Earth passes through that debris trail, every year we can get a consistent, good meteor shower.
There's also, I mean, the stream of debris is patchy on its own.
Yeah.
And we're not guaranteed to be going through the same section every time. So I think rates go up and down. But you need to have that thing going on and on. You want to replenish it. It makes you wonder about like how long the comet can last. How long can how much material is thrown out behind it compared to how much material makes up the comet itself. I'm sure someone has looked into that stuff before, but you can make guesses about structure and composition that way.
Well, pretty vague guesses, but guesses nonetheless.
Ooh, a question from Katie. Will the Lyrids be visible from the city in a suburban area?
That's a great question. Do you want to handle this one?
Well, it depends on the suburban area that you live in. Suburban Toronto, suburban huge metropolitan, probably not. But maybe suburban Ottawa would be okay. Where I live, Ottawa is pretty small. And more importantly, Ottawa doesn't have any cities right next to it. So once you leave Ottawa, you're in farm fields, whereas once you leave Toronto, you're in other cities. So it might depend on the suburbs that you're in, and it might depend on the type of lights that your suburb uses. In general, I would say not very good. You would get a few of the, I don't know what the rate is, but let's say the guess is something
20.
Like, it's 20?
It's 20, yeah.
20
per hour. 20
per hour.
It's average, yeah.
Average meteors of 20 per hour in good light, in dark skies.
Yeah.
Then my guess, in a suburban area, you're going to get 5 per hour or 6 per hour. That's just a guess, though. What do you think, Ryan?
I have a story. every good.
Did this story also end in heartbreak for you?
No.
Oh, okay, all right.
Not this time. So it was the Perseids, which is in August, and I really wanted to see them. The skies were clear, but my wife and I, we live here in Toronto. And so we said, okay, well, why don't we just go for a random drive at 2 a.m. and go to darker skies?
Right.
And so we did. We drove up about 45 minutes to a small town a smaller part of the city called Caledon in the mega city. So a little bit north of Brampton, where Jesse's from.
Brampton.
But so we sat on the side of the road and looked, and I wanted to try and take some photos of meteors. I didn't get a single photo, but basically what I can tell you is we saw maybe a dozen.
Okay.
Over a period of about an hour and a half. And that's not bad.
That's not bad, yeah.
The point I want to make to Katie is that I would consider kind of a suburban type environment, but darker, because we weren't in an actual city. We were on a side road around a city. So we had a lot of lights from the big city that blocked out a lot of the meteors, and we only saw a few. The way I see it is you can always go out and take a look, sit for half an hour, look at where they're going to be. And sometimes you just get lucky. You get a really bright one that you will be able to see, right? Because not only do meteor showers, of course, bring more meteors, they often bring a couple really bright ones, a couple really dim ones, right? It's a big mix, and there's really no telling what you're going to get. So go out, give it a look, and at worst, you'll get to see Venus and some nice constellations and what's left of that comet if you have a big telescope. I don't know.
Yeah, it's suburbs are tough, but it's easier, right? I mean, if you really want to get a good meteor shower experience, you got to put a bit of a commitment into it. You got to drive for an hour-ish. If you're in a city, you got to drive for 45 minutes to an hour. You got to prepare for it, so you got to wear good clothing, like dress for the temperature, dress for a few degrees colder than the temperature, just in case. You need flashlights, you need a good cell phone, you need food just in case. Let people know where you're going. Prepare for it. It takes a bit of a commitment, but it's worth it. It's definitely worth it. Even if you have kids, even young kids, depending on their temperament, they're going to enjoy it. It's an adventure. Treat it like an adventure. Like, kids, I know it's normally bedtime. Normally we're doing this, but today we're going on an adventure. We're going to go see.
Treasure hunt.
Yeah, it's a treasure hunt. Absolutely. It's wonderful to see. And the suburbs are okay, but the dark skies are the best.
So Jesse, we're already at the top of the hour.
It's too easy to talk to you, Ryan.
Yeah. So I want to, it is easy to talk.
Wait, there's questions
for you and I, and time flies when you're having fun. Yeah, we got a couple questions in the chat. We could take a look at that. Do you want to look at that?
How listening to meteor pings work? From Jim.
Sorry, what was it?
So Jim has posted in there, because I was wondering about how meteor pings work.
Oh, meteor pings. Yep.
When it enters the upper atmosphere, it excites the air molecules, producing a streak of light. Yes, okay, blah, okay. So ionized trail may persist for less than 1 second. This trail is capable of reflecting radio waves from transmitters located on the ground. Okay. Oh, interesting.
Cool. Meteor pings.
Meteor echoes or meteor pings.
Well, there you go.
That's super cool. Thanks, Jim.
Oh, one other note in the chat from Peter Hutchinson. Hope there's reporting on how much clearer the atmosphere is during the pandemic and measurements. Pollution's way down from big cities. Yes, it is. Nighttime effects on light pollution. Is it less with fewer airborne particles to reflect city lights? I would think so. I haven't seen a difference personally, but I would think it would make a difference. Less smog, less pollution, less junk in the atmosphere to reflect light anyway. I mean, light, the lights that we have reflect up into the sky anyway. So it's not going to be a huge improvement, but
I think that the way I would see it is, less pollution, clearer skies, stiller skies with less particles means you can see through more, for sure. Yeah. I guess the way I would frame it, Ryan, is I would call that a well-formed hypothesis, but now I'm interested in seeing the numbers.
Yeah.
Let's go measure it. I wonder, and so I guess that's basically what Peter's asking is, I hope there's someone going to be reporting on this. I also hope that we could talk, because skies are constantly under danger, both from light and pollution and satellites. So
Starlink, yeah.
Being able to measure and say, look how much greater it is when this is happening, or look how much better it is when this is happening. Yeah, I'm interested too. Good question.
Yeah. All right, well, we're going to Jesse's research, because that's what I really want to talk about. So I alluded at the start that it was about quasars, this big fancy word. Jesse, what is a quasar? Help us out.
Okay, I have a a presentation. Can I share my?
Please, yeah, you
Okay.
just share your screen.
Okay.
Everybody will
Click
see it
this.
instead of us. There you go.
Okay. All right. There we
works.
go. Let's see if this
That's
works.
beautiful.
Oh yeah. I just press play. Okay. So this, you can see the date. So I just pulled this up. Sorry, everybody. I kind of did this a little bit last minute. This is an older presentation of mine that I did, I think, for the Ottawa crew. So Chris Tarrant, you would have seen this before. Just a synopsis of the research that I did. So I worked at York University in grad school, and I studied broad absorption line quasars. And this in the background that you're looking at right there, that is an animation of what a quasar could look like, based on going theories and models of what a quasar should look like. But what exactly is a quasar? Well, let's start with a galaxy. So here is, I think this is, oh, I can't remember. I know that this is an animation, but I don't know which galaxy it's an animation of. But anyway, this is, let's call this just a random disk galaxy. So it has a bar in the middle, it's got spiral arms, there's lots of stars. You can see the red H2 regions, star forming regions. You can see dust, you can see bright blue light, you can see that the dense core in the center, and it gets less dense as you go out. A standard galaxy, a galaxy like ours, a major galaxy, would be about 35,000 parsecs across, or about it depends on the galaxy you look at. This is just measurements for our Milky Way. I can't remember how big Andromeda is a bit bigger, right, Ryan?
Yeah, almost twice the size.
Yeah, okay, there you go. Andromeda is about twice the width. But the reason I'm putting the number up, and I just chose the Milky Way number, is because I want you to get a sense of scale here, because 35,000 parsecs or 100,000 light years is a rather large space. And it has hundreds of billions of stars in it, and planets and gas and dust and all that stuff. It's a very big thing. And all the light you're seeing is mostly from stars and glowing gas, okay? So now, right at the center of a large galaxy like the Milky Way, you're gonna find a black hole, a specific kind of black hole, a supermassive black hole, which is what SMBH stands for. Now, there are many black holes within a galaxy, but they're all stellar mass. They're smaller in mass, much smaller in mass, hundreds, like 100, 200 times the mass of the sun, whereas a supermassive black hole is millions or billions of times the mass of the sun. So they're like big honking things, lots and lots of mass. And
Supermassive.
They are, in fact, they are supermassive. And the idea here is that they're only found at the center of the big galaxies, and the galaxies and the black holes probably evolved together. The galaxy formed around the black hole, and they're probably linked in their evolution in some way. And so there's actually a really interesting relationship that you can predict one of the masses if you have the other. So if you know, say, the mass of the galaxy, then there's a really, well, not a super strong relationship, but there's a trend in the literature that shows that if you know the mass of the galaxy, you can predict the mass of the black hole at the center. And that's why we think that they evolved together. There's some relationship between the two.
Oh, cool.
Yeah. So how does that happen? Why do the mass of one predict the other? Well, that's kind of sort of what my research was about. So right at the center where the supermassive black hole lives, that black hole can either be really, really active or really, really not active, or quiescent. And there's a question I can't see the question, Ryan. You'll have to read it out to me.
It's just Chris saying that you're using the same slides that you presented at the Rask Ottawa Center.
I told you, Chris. I already.
Yeah.
Now we get to share what awesome stuff happens in Ottawa with the rest of the country. So the supermassive black holes at the center of galaxies, if they're eating, if there's stuff falling onto them, then they'll be bright and active. And if there's nothing falling onto them, then they'll be just dark and dormant black holes. So we're going to zoom in to the center to look at what an active one looks like. Okay. Zooming in. Here we go. And I hope this cool video. I have this. Yeah, there we go. So this is a video, an animation of what it would look like if a black hole was actively eating. So there's, let's say, a whole bunch of gas and dust and stars and stuff that got close to the black hole and is now basically circling the drain, in a manner of speaking. It's trying to fall onto the black hole, but there's too much stuff there, and and it kind of backs up like not all the things can fall onto the black hole right away. It's just like when you pull the plug on your tub, not all of the water can go down the hole at the same time. It creates a whirlpool, and that the same thing happens here. And that disk of stuff, we call it an accretion disk, gets very, very bright, really, really bright when it's really active. Now, to give you a sense of scale here, this is only 1 parsec max. That's like 1/35,000th of the size of the rest of the galaxy. But that disk of light can actually, in a quasar, which are the brightest versions of this, can be brighter than the entire galaxy. So that little tiny 1 parsec section of the galaxy can be brighter than the entire galaxy itself. It's an insane amount of energy. And we call that a quasar. Now, you can have less energetic versions of that. Our Milky Way's supermassive black hole is not really active. There's a little bit of stuff around, but it's not an active galaxy. But M87 is an active galaxy. That quasar, or sorry, it's not a quasar. That active galactic nucleus is actively eating, and there's like a big jet shooting out of it. I'm sure people in RASC have seen that before. Oh yeah, okay. Oh man, I have so much to talk about. What time is it, Ryan?
You're at 11:07.
Okay,
I need 2 minutes left.
Okay, so
no, I'm just kidding.
I'm going to tell you exactly. I'm going to skip all the graphs and stuff, and I'm going to tell you about exactly what I was actually studying. So there's the picture of the disk, of the accretion disk surrounding a black hole, super bright. I'm going to draw a schematic on top of it. So like that's our disk, and I'm going to change our orientation so we're looking at it from the edge. Okay, so the black hole is right at the center, and we are looking at edge on to the disk of material that's swirling around it. And a lot of light comes off of that disk, but there is also wind that comes off of that disk. And the wind, it rises above the gas material, the plasma that's there, rises above the disk and then gets blown away by the brightness of the disk. The disk is so bright, there's so much energy in that disk surrounding the black hole that it literally pushes with its light, with its radiation, it pushes it at really, really high speeds. And we're talking like 5 or 10% the speed of light, shooting huge amounts of gas way out away from the quasar. In fact, so far and so fast that it can make it into the galaxy itself. It can actually affect the galaxy in ways. It can, in fact, this might be one way that old galaxies are turned off. There's a lot of old galaxies that are red and dead, and black hole winds might be the things that do that.
Because they blow away the rest of the gas and dust in the galaxy, which would be forming stars?
They basically turn off star formation, yeah.
Wow.
Yeah, and so my research was to study those winds and how they change through time, which was, and there's all the things. So basically, I don't want to get into it. I'll leave it. That's the gist of my research, and the idea is that supermassive black holes have disks of material swirling around them, or can have disks of material, which then create winds that launch out into the galaxy. It's a really interesting research.
Now, question for you about that, Jesse. I'd always thought quasars, the most active galaxies, are at a higher redshift. They're much further away. Are there any that are more local, or is this something that we've only seen in the earlier universe?
The average quasar lives about halfway to 2/3 across the universe, so they're old. It seems to be an evolutionary state, meaning when galaxies were younger, they went through a quasar phase. Yeah, I know. It's like an emo phase.
I was going to say, I had a quasar phase. I don't know about you.
I don't have a lot of literature on that. But what we do know by numbers is that if you count up all of the quasars, they live about a redshift of 2 away, which is like a little over halfway across the universe. And so they're far away, but that doesn't mean that there aren't active galaxies local. Like M87 is an active galaxy. The difference, though, is that it is M87, right? The cigar galaxy?
I think so.
I think it's M87. The difference between M87 and a quasar is quasars are much more energetic. If you take all active black holes, you take all those supermassive black holes that have stuff swirling around them and are making light, there's a spectrum. There's oh yeah, look at that jet. Oh yeah, that's nice. There's like the quiet end of the active black holes, and then there's the really bright end of the active black holes. And the really bright ones we call quasars, and those really bright ones really only live halfway across the universe. So it's not that black holes can't do it right now and be really bright and active, but the brightest ones, the real bright ones, were a long time ago.
Oh, okay.
I actually don't know what the closest one is. Is it 3C273? Maybe one of the people in Rask has looked at 3C273 before. That might be the closest black hole. Ooh, I'm gonna Google it.
Now, what's the jet?
Closest quasar.
You mentioned this jet in the image that I showed of M87.
Yes. Oh, that's a whole, oh my gosh.
I opened a can of worms. Is that what happened?
It's a can of worms. I don't understand it very well. There's people who work on those jets, but it's, with all that material that's falling down onto it, you have probably a lot of magnetic fields that are being generated. You have a lot of energy that's being generated. And one of the ways that the swirling material gets ejected is through these jets. So basically it's a process I don't understand very well, but you have very high energy in a compact collimated thing shooting at one end and the other end. The short answer is I don't know how they're generated.
That's okay. I don't mean to put you on the spot. I had always thought it was something to do with conservation of angular momentum as material falls onto the black hole.
Yeah, it may also be that. Yeah, okay. I think the problem though.
Beyond me.
The problem, I think you're right. I think angular momentum plays a role, but the magnetic field thing is really a question mark in quasars right now. And well, at least it was when I was working. Okay. There's probably people working on it. The disk is permeated with weird magnetic fields, and yeah. I'm sure someone can give a better answer than that.
It's all right. A couple more questions about active galaxies.
Ooh.
Are there certain classes of them? I guess quasars are a class that are a certain level of energy, but is there some kind of, I guess, mid-level? Maybe you alluded to this already, but
there's ranges. There's like a spectrum of energy. There's a group of active galaxies called Seyferts, which is more of a historical term, and there's different kinds of Seyferts, or Seyferts might be the right way of pronouncing that. And the different kinds are seem to be related to orientation of how you're looking at it, because it flattens down into a disk. If that disk is face on to you, or if that disk is not face on to you, you'll get different kinds of spectra, and you'll be able to determine different kinds of things. There's also in Seyferts, in fact, Leanne worked on those a little bit. She worked in active galaxies in groups, in local groups, and Leanne was a colleague of ours in grad school, and she worked on, there was specific features in the quasar, in the Seyferts, I wanted to say like oxygen 6 lines, and something else that meant something specific. So there are different, there's classes in there. There's high energy stuff and low energy stuff, and there's all these little classifications in between, almost like supernova. How supernova have those like the major 1 and 2, and then a bunch of like 1A and 2B, C, and all all that stuff.
Right on.
So there's lots of different stuff.
We have a question in the chat from Don York. Does that have something to do with gravitational waves?
Oh, that's a good question. I don't know the answer to that. Gravitational waves certainly would be, like, with the amount of stuff that's there orbiting this supermassive black hole, gravitational waves got to be doing something. But I think the only way we can really measure stuff like that is when two black holes merge.
Yeah, currently the only detected gravitational waves from LIGO in the United States or Virgo in Italy are from either black holes merging or neutron stars merging.
Yes.
Or I think one might be a neutron star black hole collision as well. But basically, you're thinking of the biggest, densest, heaviest things, compact objects in the universe colliding
Yeah.
And that's creating obviously the highest energy, most detectable gravitational waves. So there probably is, like you're saying, Jesse, some connection, and there's something going on that's probably creating some pretty hefty gravitational waves, but we don't have
Probably.
the ability to detect those just yet.
Yeah, they're probably on smaller scales. Like if you had two, if you have a quasar and a neutron star hit it, maybe we would be able to detect that. Um, but if you have just that slow, you would the efficiency of accretion, so the amount of material that's actually falling onto the black hole is lower than you might think. So it's almost like a slow trickle of stuff coming off the disk and falling in.
Like
So
molasses going into a drain. I'm just thinking of fun analogies here. That's
I don't know. I should look into that. The
okay,
energy is there, and gravitational waves probably are playing a role, but I wouldn't know how they're manifesting.
okay. Then one more question, Jesse, and this is the question I like to ask people, because you know, my research supervisor always told me this. You know, why do we care?
Why do we care?
Yeah, I mean, you know, 95% of the great work that you do, it sounds really awesome, but what is it? How does it all fit into the big puzzle of the universe?
Okay.
What does this tell us about the universe?
The shortest answer I can give to that is it looks like the quasar engine plays a role in the building of galaxies, which means the galaxy that we live in and galaxies that seem to be pleasant for planets like ours, that have lots of star formation, that are young, that have lots of planets, basically lots of planets in interesting places. With that was how we got to where we are was definitely shaped by the quasar process. Now that doesn't mean that we'll be able to predict life in another galaxy based on its quasar activity, but if you want to know why Milky Way looks like Milky Way right now, then part of that story is the active phase of the black hole at the center and the evolution of the galaxy itself. So the reason we care is because you can't build a galaxy without an active black hole.
Couldn't have said it better, man. That was fantastic.
Knocked it out the park.
We'll happily answer any other questions in the chat about anything to do with Jesse's research, or just anything.
Anything. I like being stumped. I have very few answers and lots of, oh, that's a good question.
Yeah, right. That hey, I didn't think of that one. That's we gotta somebody smarter than me knows the answer to that. And hey, that's what I do all the time, right? So
yeah.
We do have somebody in the chat, Mike Ashby. Doesn't the debris trail have a beginning as to where the comet began evaporating and then eventually disappear? Doesn't the debris trail have a beginning as to where the comet began evaporating and then eventually disappear? Yes, I think it would. I think if you could see in here, I'll try and bring up the
logically that makes sense.
I got to kick back a few pages, but yeah, I think it makes sense that, you know, if you sorry, I'm looking at a lot of stuff here, that if you could see where in its orbit the comet starts to disintegrate, and kind of rather where the debris trail ends up. But the thing is that comets, even as they give off dust and slow, they are kind of breaking apart. All of that dust remains in the orbit of the comet. So as the comet breaks up, all of those individual chunks should also be roughly in the same orbit. Does that make sense, Jess?
Right, but way out at the end. So when the comet, when it's far from the sun and it's no longer sublimating, way out at the aphelion, there would be a lot less dense material. Like the trail would be very, very not dense out there, right?
Yeah, like, it would probably spread out a little bit more.
Yeah, like if you go all the way around the orbit.
Yeah. I guess what I'm getting at is that as the comet's breaking up, there's not a lot of active forces that are pushing those individual chunks off of their orbits, at least initially. Maybe as it rips around the sun, there's a little bit of a little bit more.
I think that the materials would be small enough to
thing.
be affected by radiation pressure.
Yeah, exactly, right? So as it
Yeah.
goes around the sun a little bit more.
Oh, yeah, the annual showers, Mike. Yeah, we're thinking like, so when you create the debris from the comets as they go around, we're trying to figure out where does that debris go? Because you're asking, there should be a start point and then an end point, and then it would be if you're really far from like if you go all the way around the orbit of the comet and just count up all the material, say you could do that with a spaceship.
Yeah.
Do we expect, here's my question, do we expect there to be an even amount of debris all the way around the orbit, or would there be more debris close to the sun and less debris at the farthest point?
Oh, interesting. I think it just depends on where in the orbit you're at. That's a good one to think about.
I've never actually thought about that before.
Now I'm gonna go think about that all night. Thank you.
Ooh. Any idea whether our Milky Way went through a quasar phase? Okay. I don't know.
Jim, for that question. And thanks, Mike, for your question as well. What do you think, Jesse?
Okay, so I don't know, and I'm Googling it right now because I recently saw an article about it.
Okay, you look at that. I'm going to briefly talk about it's Hubble's 30th anniversary coming up in a few days, and so I actually pulled up a few of my favorite Hubble images just to share with all of you lovely people. It's going to look terrible because it's on my screen, as instead of actually on your screen that you can, but you'll go and you'll download it and it'll look really nice. So the first one I wanted to start with, the pillars of creation. I'm picking just kind of my favorites over the past couple decades. But the pillars of creation, the Eagle Nebula, an absolutely iconic image. Most people, when they think of the Hubble Space Telescope and what it's done, this is the image that they want to talk about. This is the image that they look at. This is pillars of where stars are being born at an incredible rate. Their the radiation from the star is blowing away the leftover gas and dust in this cloud, and will eventually deplete it of gas as it forms a ton more stars. And pillars of creation alludes to the fact that this is how stars are born, in these giant columns of gas that are far bigger than our solar system. Thousands of stars form, and maybe eventually planets, and maybe eventually life, which is kind of fun to think about. So that's the pillars of creation, kind of the iconic one. My second favorite, and I know, Jesse, you like this one a lot.
Which one is it?
Ultra Deep Field. And I love the thought of this one. If you take a grain of sand and you hold it at arm's length and imagine how much of the sky that covers, this is what Hubble saw in that amount of sky. The region of sky blocked out by a grain of sand held at arm's length. And it took hours and hours and hours and hours of imagery to capture this. And that also means that it doesn't matter where you put that grain of sand, whether you put it up over your shoulder or behind your head, on any part of the sky, northern hemisphere, southern hemisphere, there's this many galaxies in every little grain of sand sized part of the sky. And so that's why I love this image. It also shows you the different types of galaxies, the colors from the redshift, right? Galaxies that are more distant appear redder because they're moving away from us more quickly. As the universe expands, there's so much depth and understanding to this image. You get light being bent by clusters of galaxies from Einstein's relativity. All kinds of crazy stuff is going on in this image that you don't necessarily realize at first because you're so lost in the number of gorgeous galaxies, each one of these galaxies having hundreds of billions or trillions of stars and planets and all kinds of cool stuff. Did you get your answer, Jesse?
I don't. Oh, that's a good question.
I'm going to do another Hubble image then. Did you want to address it?
Here's my short. So I remember there being a little bit of work done where if you look above and below the planes of the plane of the Milky Way, there are some high energy. There's traces of what look like if Sagittarius A star was active, it may have had those jets and shot lots of material up and down out of the disk. And there seems to be traces of that. So I think whether it was a quasar or not is hard to say, especially because we're talking about a time frame. If it was a quasar, it would have been a long time ago, probably before the Milky Way was as big as it is now.
For a lot of collisions with smaller galaxies,
merge it together into a bigger one. But if we reframe the question slightly to be, was Sagittarius A star ever active, like really active? The answer is probably yes, but potentially not as active as, probably not as active as the quasars that I studied.
Well, sure, you were looking at some of the most luminous, high redshift in some cases. Were there any high redshift ones you looked at, or?
Depends on what you mean by high redshift. The highest redshift stuff was, I looked at ones as high as like 4.5, which is, I'm trying to do the math in my head. So that's like, that's like 11 billion light years away, roughly.
Just a little far.
It's pretty far, yeah. There's some people who look at like 6.5 and 7 and 8, and those people are crazy.
So so it seems that there's a whole, there is a whole spectrum of active galaxies, and that if it's part of a galaxy's evolution, the Milky Way was probably, or Sagittarius A star was probably active at some point, but maybe not to the quasar level where we can see traces of that activity.
Exactly. I think that would be my best answer right now.
That's great. And look at that. I even summarized it properly. I'm amazed even myself.
Who would have known, Ryan?
I amaze even myself. Okay, we've got one more Hubble image that I want to show, and this is actually my favorite image in astronomy. So I'm going to shamelessly.
Your favorite image in all of astronomy?
All of astronomy.
Ooh.
And part of it was that when I did my master's, I was focused on this particular galaxy in my research. So you can probably guess which galaxy it is. It is Andromeda, Messier 31. And this image is not the whole galaxy. And you're probably thinking, okay, well, why is it not the whole galaxy? Why is this
not even worth looking at?
Well, there you go. You might be asking, Ryan, why is this your favorite image in all of astronomy? And it's that, we as astronomers, as you and I, especially Jesse, as science communicators, we spend a lot of time talking to people about just how vast the universe is, about how big things are, and I'm going to pull up me for this, how big things are, how many stars are in the Milky Way. I can say that, there's 200 billion stars in the Milky Way. And I say that to kids and they're like, wow, that's a big number. But they don't really have a grasp of just how many stars that is or what that really means, right? They see a galaxy in the sky and it's a beautiful picture of spiral arms, and it doesn't really show how many stars there are. This picture shows how many stars there are because we can zoom in on it. And I purposely got a high res version of it so that we can zoom in and actually see all the individual stars that make up the Andromeda galaxy. And so look at that. Every single dot in this image is a star that's part of the Andromeda galaxy. One of those, and I think Andromeda's got almost 1 trillion stars.
Oh my gosh.
Counted at this point, or estimated at this point. And you can see all of them. And if it doesn't matter where in the galaxy we look, we can look in the darkest region of the galaxy and we can see just stars everywhere. This is the dark part of the galaxy and there's stars everywhere. We can look in the core, in the brightest section, and we see just tons more, so many that there's no dark space between them, right? By the way, these are field stars. These are stars that are in our galaxy in front of Andromeda. But this is why it's my favorite image, is you can say that this galaxy has 1 trillion stars, but this picture lets you see it. It lets you see it. And that's,
what makes me I want to like count them all. Like, I know that sounds crazy. So like, I wonder if there would be a way to actually count them all, like with some computer program or something, so you could literally get an actual number.
Well, I will tell you, part of my research was finding star forming regions, H2 regions. And so there was actually some code that you would run it on images, on H alpha images of the galaxy, and it would basically best fit all of the star forming regions, all of the H2 regions. And
like count them up?
Yeah, basically.
Ah.
And it would also categorize all the emission from them, so you could do kind of a global picture of the galaxy to get a sense of how much star formation was happening, how many stars, because it's O and B type stars basically, how many of those stars are actually forming, and get a sense of the total stellar mass that's forming in the galaxy year over year, to kind of give us ideas about galaxy evolution. Um, and so I can't imagine that there's something similar for counting stars, but it'd be really tough because when you look at this image and you say, okay, well, we're down to counting pixels. But by the way, this is not the highest resolution image of this. It's I think the highest resolution version is like 300 gigabytes. This one is, I think, 3 or 4 gigabytes. It's this third highest resolution one because it's the first where you can actually go in.
That image is 3 gigabytes.
Yeah.
Holy crap.
So you can actually go in and see all the stars, but lower res versions, you can't really see them all up close. And the highest res version, they actually, you want to hear something funny? You see this here. That might be a galaxy that's behind Andromeda. There were several dozen, maybe hundreds, I don't know the exact number, of galaxies that were discovered because of this image that were actually behind Andromeda, that they found by just literally looking straight through the galaxy, which is kind of hilarious and kind of amazing. So this is my favorite picture.
So you may have mentioned
I love
this.
to share it with people because this is why I love being a science communicator. And this is why I do planetarium work, is because I can show people this stuff. I can learn to explain it. I'm ranting here. I can learn to explain it as well as I possibly can. I can become the best explainer that there ever was and use words like explainer, but I can't, but until I show people, until I can let somebody discover it, it doesn't do it. It's the picture's worth 1,000 words, right? And that's why I love this image. And that's how I'm going to celebrate the 30th anniversary of Hubble with my favorite. Do you have a favorite one, Jesse?
From Hubble? Or
yeah, like the birthday thing. Did you want to talk about the birthday thing?
Oh yeah, there was. I don't have the link. Do you have the link ready?
I'll pull it up. But
maybe it's on my Twitter.
Talk about it.
Because it's the birthday of Hubble, they have this cool web app or applet or whatever you would want to call it, where you just you put in what did Hubble see on your birthday? There it is, right there, and you can get an image that was taken on the day that you were born. Not the year that you were born, but the day of the year. So select your birthday.
When's your birthday, Jess?
October. You should know. Come on, man.
I do, but I'm not gonna.
16th. I don't want to embarrass you, so I'm telling you. There you go. And then, the Ring Nebula.
That's a good one.
I know, right? I got a good one. And so that was in 1998. Okay, 1998.
I'm just going to post the link in the chat so anybody can go and play around with this.
And then post it on Twitter.
I should.
Yeah. No. People in the chat, if you have Twitter, post your picture.
Oh, post your picture on Twitter.
Whatever picture you have, if you have Twitter or Facebook or whatever, post it and get other people to do it. It's fun.
Well, there you go. So for the 30th anniversary of Hubble, that's a really fun one to do. So is that Ring Nebula one of your favorites, I guess? Or is there another picture that really sticks out for you?
I don't have one that sticks, at least not off the top of my head. I do love images of bubbles. I like the Ring Nebula because I like things that are round but look flat with a ring.
Okay.
Like, because bubbles in space or bubbles anywhere, even just bubbles that you like blow with soap, they're round spherical things, but the edges look thicker because you're looking through more stuff. And where it's, and so bubbles are weird in space. So I like looking at them. I don't have an image off the top of my head from Hubble. Maybe the deep field, Hubble deep field is pretty cool.
Yeah, I mean, yeah. You said to me before we started, you really liked the deep field.
Ooh. Look at that. It's incredible. God, Mike Ashby in the chat got Comet Ice on. The great letdown.
the greatest letdown of my news media career. The Comet of the century, Comet Ice on.
There's a talk from Chris Gaynor. He's got the new director for Hubble that actually named the pillars of creation.
Oh, that's fantastic. Yeah, and the link's there in the chat. Thanks,
Awesome.
Phil, for that.
Very cool.
That'll be a fun one to check out. So I think we're at 11:35 at this point.
Friday at 7.
That's when the chat is. Yeah. So.
Oh my gosh,
God,
Peter.
I thought Kahutek was the comet of the century. Not many people will get that joke unless they were the older crowd. But
I do not get that joke.
Yeah, Comet Kahutek was also one of those like famous fizzled comets.
Okay. Wait. So Peter Hutchison just said, try finding a star that is the same distance in light years as your age, then you can see the birthday photons. Holy crap. I've been talking with people about space forever. I have never thought about that. Oh, that's cool.
No kidding, eh? See, now
there's huge catalogs of stars out there.
Oh, that was a nice one. Yeah, look at that.
So
I wasn't alive when that happened, so I'm not old enough yet.
Big catalogs of stars that you can order by distance. So that shouldn't be too hard to do. I'm going to look into that. That's cool. Thanks for that.
That sounds kind of fun.
We might, it's late. Sorry. We might need to.
No, that's okay. We Jesse and I could probably talk all night about all the different things that, he does and we are interested in and curious about, because that's kind of what we do. We love to talk about the things that we're passionate about, and we're both passionate about space and have been for a really long time. So we are probably going to finish on that note. It's getting pretty late, at least for us here on the eastern side, or the central part of Canada. So we're getting a little sleepy, but I want to thank everybody for tuning in. I really, I'll be glad that Jenna's back in a couple of weeks to do this with me, but
a lot of work.
It was a lot of fun. Luckily having my good friend Jesse on really makes things easier. But thanks a lot, everybody, for the questions and for your time and for being patient with us as we got through all this fun stuff. So clear skies to everybody. Jesse, thank you so much for joining us. That was a lot of fun to hear about what you were working on and kind of what you're up to. So
you're welcome. Thanks for having me.
Follow Jesse at Jesse Rogerson, or you can see my info there on the screen. Thanks everybody for the questions and for hanging out. Go check out the meteor shower. Go see Venus. Go look for what's left of Comet Atlas. And have an amazing night. Thanks very much. Signing off.
Good night, everybody.